This is the fourth module or section in our chapter 38 on general relativity and astrophysics, and this section is 38.4. We attempt to give you some idea of what the mathematical theory of general relativity is. Now, to take you back just a little bit, this mathematical theory was developed actually by a mathematician named Riemann, where he developed differential geometry of curved spaces. This was done back in the middle 1800s, and Riemann was one of the most famous and brilliant mathematicians that has ever lived. And he, of course, was working not on things like general relativity, but he was working on things like if I have a line that's curved or a surface that's curved, and this line or surface is in three-dimensional flat space, then I can talk about a curved space, like a bent piece of plastic or something. And I can talk about the surface of that or a line on it, even though it's in a larger dimensional space. So he studied n-dimensional spaces that were embedded in m-dimensional spaces. This laid the groundwork for what Einstein was to do 50 years later. Now, the foundational aspect here that you have to do mathematically to study general relativity is to study what is called the scalar product, or the metric. The metric is something new. It's a 4x4 matrix where mu and nu go 0, 1, 2, 3, 0, 1, 2, 3. So this thing has 16 parts. This would be G naught naught, G naught 1, and so forth, G 1 naught, G 1 1, and so forth, and there would be 16 elements to this G mu nu. Well, normally, this G mu nu, the metric, is something that's very simple. Usually, G mu nu in relativity is equal to 1 minus 1 minus 1 minus 1, and all of these terms are 0. That tells us that when we take the scalar product of two vectors, the scalar product, A dot B, is defined as G mu nu, A mu, B nu, summed over mu and nu, which is going to be what? Well, the only terms that are not 0 are the terms G naught naught, this would be G naught naught, which would be 1, A naught, B naught, and then minus A1, B1, minus A2, B2, minus A3, B3. Now, when we look at space and time, those two vectors might be something like CT, X, Y, and Z, and then we would get here this vector, let's call it X. That vector X would be C squared T squared minus X squared minus Y squared minus Z squared, which is minus R squared. And so this would be X dot X. And this is unchanged. This is what is called invariant. This is a length. Now, this length is very unusual in special relativity even, because it has a minus sign. That makes it different from the regular Pythagorean theorem, which would be a square plus a square plus a square plus a square for a vector with itself. And you can see here that if CT is equal to R, then I can have a vector of 0 length, even though its parts aren't 0. This is very strange. How can something have no length, even though its components have size? Well, this is, it turns out, the way Riemann developed his spaces, because all space spatial distances and angles are defined by this function right here, the scalar product. That was because any two vectors in a space are such that A dot B is the length of the first times the length of the second times the cosine of the angle between them. Now, if I take a vector with itself, like A dot A, this becomes A, length of A times the length of A, or length of A squared, and the angle between a thing and itself is 0, therefore the cosine of 0 is 1. So this tells us that a squared is going to be the square root of this. So a is going to be the square root of a dot a. Well, now I have length and I have angle. Since I can figure the length of this and the length of this, I can now find the angle between any two vectors by taking the dot product and then dividing by the two lengths. So I can determine all angles and all lengths in the space, and this makes it what we call a metric space. Well, this is already bad in special relativity. It's kind of strange, but it's still kind of flat. It mixes up space and time in ways that make it something new invariant. Rather than length and time being invariant separately, they have a joint invariance, which is this right here. The same goes with momentum. P dot P, momentum dot momentum, or momentum squared, is E squared over C squared minus P squared, and that invariant is M squared C squared. That is the mass of the particle times what's called the rest mass of the particle times C. And so this shows you that if I look at momentum, it is also can be written in terms of an invariant product, kind of like it's like a Pythagorean theorem, but with some minus signs in it. Okay, so this was bad enough back then, but if your space is curved, then in fact this metric takes values that are not equal to 1, minus 1, and 0. This gives us length and angle from a new point of view. Particles, as well as light itself, will follow the shortest distances, and those distances are called geodesics. A geodesic in a space is the shortest distance from one place to another. And Einstein's equation then relates the metric for the space, which tells us how it is curved, to what is called the energy momentum tensor, T mu nu. Now that energy momentum tensor, T mu nu, tells us how much energy and how much momentum is in different places, and that is then related in Einstein's equations to the metric, or the curvature of space. So the curvature of space is defined by the presence of energy and matter in that space. These equations are extremely complex, and they actually determine how things are bent and warped around objects, or where we have energy density, and therefore how things follow curved paths that appear to be attractions. Well, that theory is still not reconciled, as I said earlier, with regular quantum theory. It's very difficult because you're altering your whole infrastructure of space and time with this theory. So we still do not know how to integrate the gravitational force, a la Einstein's theory of general relativity, with our other forces, which are the strong force, the electromagnetic force, and the weak force, which are much better understood, much more well understood in our quantum theory and what is called the general model. We will talk about that later.